All right, welcome back, everyone. Today we're diving into a high-yield crash course on polymer structures to get you absolutely ready to ace your upcoming quiz. If you've ever wondered what makes a plastic rigid like glass or stretchy like rubber at a molecular level, you are in exactly the right place. Here's our roadmap for today's explainer. We'll cover the glass transition temperature, free volume and deformation, the thermodynamics of polymer chains, polymer crystal structures, forming lamellae and spherulites, and we'll wrap up with measuring polymer transitions. Let's get right to it. Module 1. The glass transition temperature, or TG. We're starting off with the absolute foundational vocabulary for this subject. So here's the formal definition you really need to lock in. The glass transition temperature is the temperature at which an amorphous polymer changes upon heating from a hard glass to an elastic liquid or solid. If this pops up on your test, just remember, TG applies specifically to the amorphous regions of a semicrystalline polymer. It's that precise moment where long-chain segments suddenly get the freedom to move around and change their conformation under stress. To put this into perspective, look at these modulus values. Below TG, a polymer's tensile elastic modulus usually sits around 2 to 3 gigapascals, so it's super hard and stiff. But the second you cross that temperature threshold, the modulus plummets to roughly 1 megapascal. You are literally losing 3 whole orders of magnitude in stiffness over just a few degrees of heating. That is absolutely crucial for real-world engineering. Moving right along to Module 2, free volume and deformation. So what actually allows these chains to start moving when they heat up? Well, it all comes down to a concept called free volume, which is essentially the difference between the actual volume the molecules take up and the total volume of the material. Check out the data here. In the glassy state, before we hit TG, this fractional free volume is essentially flatlined at a constant value, right around 0.02 to 0.025. But look closely at what happens exactly at TG. It just shoots upward.
You know, the best way to anchor this in your mind for the exam is to think of free volume as a polymer chain's elbow room. When cooled below TG, the material is just too crowded. The chains are stuck. But crank up the temperature and you get more elbow room. And more elbow room literally means greater segmental mobility, allowing those chains to wiggle into different physical conformations.
Which brings us to a really interesting question. Once these chains finally have that elbow room above the glass transition temperature, how do they actually uncoil and straighten out when you apply stress? You might instinctively think the chains just stretch out like rubber bands. Actually, scratch that. While minor bending and stretching do happen, the real hero here is bond rotation. As you can see in this molecular model, it's the atoms physically rotating around their chemical bonds that generates those massive strains in polymer deformation. They literally untwist the entire molecule. All right, on to section 3, thermodynamics of polymer chains. Let's see how all this mobility ties into the thermodynamics that dictate how these chains behave. Now, nature always wants to be in the most stable state possible. We can see this through the simple thermodynamic model where the change in free energy, delta G, equals delta H minus T delta S. Basically, polymer chains inherently adopt whichever conformation minimizes their free energy. But how they pull that off completely depends on whether they're packing into a crystal or just acting as a single chain. Let's break that down into some high-yield takeaways for your quiz. To minimize free energy, single chains maximize their entropy by forming random coils, kind of like a messy, tangled bowl of spaghetti. That's exactly what you find in liquids, rubbers, and amorphous solids. Crystals, on the other hand, take the opposite approach. They minimize their enthalpy by packing tightly together to maximize intermolecular bonds. Sometimes they even have to form complex helical shapes just to fit together perfectly. So test tip, firmly associate crystals with low enthalpy and amorphous random coils with high entropy. Module 4, Polymer Crystal Structures. Let's take a look at what these energy-minimizing crystals actually look like in the real world. Polyethylene is your classic textbook example of this packing behavior. Notice how incredibly tightly these chains squeeze into a geometric unit cell. By organizing themselves spatially and leaning on those intermolecular bonds, they're successfully minimizing their free energy. But here's the catch. Not all polymers can pull this off. Definitely write this down. Tacticity dictates crystallinity. For a polymer chain to pack into a crystal, it has to have a regular shape. Isotactic polymers, where all the side groups are on one side, they can crystallize. Syndiotactic polymers with alternating side groups, they can crystallize too. But atactic polymers? No way. They are completely irregular, and those bulky, random side groups ruin any chance of tight packing.
And this diagram perfectly illustrates that rule. Because PVC has that regular, alternating syndiotactic arrangement, the molecules can pack beautifully into a neat, rigid crystal lattice. Another awesome example to keep in mind is nylon. For nylon 6,6 and nylon 6, the strict structural organization is totally driven by powerful hydrogen bonds. See those dashed lines? Those represent the hydrogen bonds creating super dense crystalline sheets. When you have intermolecular bonding that strong, the chains are locked in, which dramatically drops the material's enthalpy.
All right, Module 5, forming lamellae and spherulites. Let's zoom out a bit and look at the structural hierarchy of how these crystals actually grow. You're going to want to memorize this step-by-step hierarchy. First, our random molecular coils fold up into helices or extended chains. Next, those chains pack together to form flat plates, which we call lamellae. Keep in mind, these lamellae still have some amorphous regions mixed in. Finally, those lamellae grow and organize into large, macroscopic spherical structures known as spherulites. Oh, and a quick kinetic note for the exam, thicker lamellae and larger spherulites tend to form at higher temperatures. And that brings us to our final module, Section 6, Measuring Polymer Transitions. Because at the end of the day, engineers need to know how to actually measure these properties in a lab. Make sure you keep these two methods straight for the quiz. It's a super common question. We have DSC, or differential scanning calorimetry, which measures heat flow. DSC is your go-to for finding the glass transition temperature, the melting transition, and the overall degree of crystallinity. On the flip side, we have XRD, or X-ray diffraction. XRD is used specifically to determine the degree of crystallinity by observing how the crystal lattice structure scatters X-rays. All right, we've covered a ton of highly testable material in this explainer today, from the molecular elbow room of free volume all the way up to macroscopic spherulites. So I'll leave you with this thought to chew on before your test. If free volume is the ultimate switch that controls whether a plastic acts like a rigid glass or a bouncy rubber, how could you intentionally engineer those molecular bonds or the chemical composition to perfectly tune that transition and invent a completely new industrial material? Good luck on your quiz, everyone, and keep exploring.